Hello and welcome back to the HIV RNA Test Guide.com YouTube channel, your trusted source for HIV testing with over 4,500 HIV testing labs across the United States. For more information, check the link in the description of this video or the bio section of our channel.
Welcome to the Deep Dive. Our mission today is, well, it's absolutely critical. We are going to be cutting through all the noise surrounding global public health to bring you the essential insights and the context for the pivotal news emerging this November 2025. And it's all about the long, relentless quest for an effective HIV vaccine.
It really is a challenge, unlike almost any other in modern medicine. I mean, despite decades of just massive effort, the numbers, they're still sobering. Even as we get into 2025, you're looking at 40.8 million people living with HIV globally.
And that's not the static number.
No, and crucially, we are still logging 1.3 million new infections every single year.
Which puts the timeline for success in really stark relief. The global community is aiming for that UN Sustainable Development Goal 3.3, which mandates ending AIDS as a public health threat by 2030.
Right, and that date is coming up fast.
It really is.
And what our stack of sources reveals is the story of incredible, almost paradoxical contrast. On one hand, the scientific acceleration is just stunning. Researchers are using these cutting-edge technologies that they've fundamentally changed how we even approach vaccine design.
On the other hand,
But this scientific velocity is set against a backdrop of severe political instability and financial headwinds so disruptive they could genuinely threaten to wipe out years of progress toward that 2030 goal.
exactly. We've got these detailed reports on next-generation vaccine platforms, including some unexpected and frankly fascinating partnerships like Amazon scientists working with Moderna. We have clinical trial data that shows immunological differences between participants that are so massive, they're forcing a complete rethink of how we design these prevention tools. And then we also have these essential qualitative studies detailing the very real fear, the stigma, and just the bizarre rumors that trial volunteers face on the ground.
Yeah, in places like Tanzania.
Exactly.
And then tying all this together are these urgent reports on the geopolitical and financial chaos, specifically detailing massive shortfalls in global funding and the fallout from some deliberate disruption in U.S.-led global health aid earlier this year. It's the full picture, scientifically brilliant, epidemiologically essential, and politically very, very precarious.
Okay, let's unpack this, and let's start with the promise, with the science.
To really appreciate the breakthroughs, I think we have to start by framing the sheer difficulty of the target, and that's the HIV virus itself. HIV is often called a master of disguise, and, well, for good reason. From the moment the epidemic began back in the 80s, infecting over 75 million people are conventional vaccine approaches.
Well, does it work for measles or polio?
Exactly. They have just failed. Completely.
And the reason for that failure is that HIV is almost perfectly designed to evade a standard immune response. It's got layers of protection, right? For instance, the outer spike of the virus, that envelope protein, it's constantly shifting its shape. It's just a series of transient, confusing targets.
Not only that, but it cloaks itself in what scientists call a glycan shield, a dense layer of sugars. And this makes the viral surface practically invisible to most of the antibodies your immune system can even produce.
So standard antibodies, the ones that usually target a fixed protein shape, they just can't get a grip.
They just slip right off that sugar coat.
Yeah. So if the virus is so good at hiding, how do you force the immune system to finally see it? Research has identified one potential pathway: the development of broadly neutralizing antibodies, or BNAbs.
These are the immunological superheroes?
The superheroes, I like that.
They really are. BNAbs are special because they are broad enough to target parts of the virus that don't change, the vulnerable fixed structures that are usually hidden away. They can recognize and neutralize up to 99% of all known global HIV strains.
99%. That's the definition of a universal vaccine right there.
That is absolutely it. But here's the massive catch. Most people who get infected only develop these powerful BNAbs years into their infection, and only after their immune system has been running this high-stakes evolutionary race against the virus for a long, long time.
Which, as one scientist put it, is just too little too late.
Far too late. Therefore, the entire modern vaccine strategy had to shift away from using weakened viruses or, inactivated parts. The new goal is what we call structural vaccinology, designing an artificial molecule that specifically forces your body to start making those BNAbs right away.
Before you're ever infected.
Before infection even occurs.
That sounds like a biological needle in a haystack operation. I mean, how exactly do you force the body to produce this one specific, powerful type of antibody?
It is exactly that. The focus is on training these rare precursor B cells, some people call them baby antibodies, which are, and this is not an exaggeration, literally 1 in a million in terms of how many you have.
Right.
And you have to stimulate them precisely. Almost everyone, regardless of HIV status, has the genetic potential for these cells. The trick is finding them and then kicking them into gear.
And this brings us to the technological breakthrough, underlying the first major piece of news we have, the nanoparticle platform. This foundational work was developed by scientists like Sergey Menis, who is now actually an Amazon scientist.
Which is fascinating.
But he built this work during his time at the University of Washington and Scripps Research, collaborating with Bill Sheaves' lab.
Right, and Menis, he engineered the key delivery vehicle, the nanoparticle platform. This is a synthetic, engineered protein structure. You can think of it like scaffolding. It's designed to physically snap together with the specific protein payload you want to deliver.
And in this case, that payload is known as EOD-GT8.
EOD-GT8. That protein is the critical molecular trigger. It's been meticulously optimized to bind specifically to those rare precursor B cells we need to kickstart the whole BNAb maturation pathway.
So it's like a very specific key designed to fit into a very specific lock on that 1 in a million cell.
Precisely. And the nanoparticle structure, that's the genius of the delivery system. The scientists were obviously thinking, okay, how do we make the immune system actually pay attention to this tiny key?
Right.
So they engineered the nanoparticle to be spherical to mimic the shape of a non-infectious virus, but it's completely safe, of course. The crucial innovation here is that this spherical structure delivers multiple copies of that EOD-GT8 protein key in a highly organized, repetitive display.
So instead of just floating one key around, it's presenting a massive target, almost like a soccer ball, covered in hundreds of keys, right?
A perfect analogy. That repetitive, organized display acts like a powerful immunological megaphone. It amplifies the signal to the immune system and dramatically increases the chances that one of those rare precursor cells will be activated and will notice it.
In the phase 1 clinical trial, using this approach, IVIG001, it actually proved this concept worked in humans.
It did, with stunning results. Back in early 2021, the vaccine candidate produced the desired initial immune response, activating those specific precursor B cells in 97% of participants.
97%.
This was the first major step confirming that this engineered structural approach was truly viable.
Now here's where the modern technology acceleration really comes in. That success immediately moved the development pipeline to the next level, mRNA. We are talking about the IAVI G002 trial, where IAVI partnered with Moderna.
Right, and they leveraged the power of Moderna's messenger RNA delivery platform, which, we all know from its ability to rapidly manufacture vaccines during the COVID-19 pandemic. The use of mRNA here, it just fundamentally changes the development timeline. It makes it incredibly fast compared to traditional protein manufacturing.
So instead of the researchers having to painstakingly manufacture the EOD-DT8 protein keys in a lab and then attach them to the nanoparticle, they are injecting the genetic instructions, the mRNA, into your cells.
And turning your body into a mini factory for the vaccine component.
That's just elegant efficiency.
It's incredibly elegant. The IAVI G002 trial is focused on using this rapid mRNA platform, not just to prime the immune response, but to follow up with subsequent mRNA shots that are designed to mature those baby antibodies further down the BNAb pathway. It's a highly targeted, multi-stage instructional process for your immune system.
It sounds like they're creating a rapid, personalized training program for the immune system, and they're using the absolute fastest tools we have today, thanks to all the lessons learned during the global push for the coronavirus vaccine.
It is an extraordinary moment. The foundational structural immunology that was built over decades is finally being married to these 21st century speed-of-light manufacturing techniques. George Washington University is collaborating with IAVI and Moderna on this new phase, which they rightly describe as experimental medicine, but it's medicine utilizing the most powerful accelerated platform we currently have.
Okay, let's pivot from those structural design challenges to the complexity of the biological response. This is where the news gets really, really interesting. Specifically, the findings from the ACT-HIV-E001 Phase 1 trial published just this November. This is where we see biological responses so varied, they force us to rethink vaccine design entirely. And it's specifically concerning sex-based differences.
This specific study, which was in Nature Communications, looked at a different vaccine candidate. It's called CONM-SOCIP.V7NV trimer protein. It's another structural approach, a stabilized trimer, based on a synthetic consensus sequence for HIV-1 group M, which is the major circulating group.
And the key ingredient that seems to have unlocked this dramatic observation was the high-powered helper molecule they used, the adjuvant.
Absolutely. They administered the vaccine alongside a very high dose of monophosphoryl A, or MPLA. Now, MPLA is a toll-like receptor 4 agonist.
Okay, what does that mean in plain language?
In plain language, it means MPLA acts like the immune system's loudest, most urgent alarm bell, a signal that screams massive bacterial invasion, and it just dramatically enhances the whole immune response.
The trial was small, just 24 HIV-negative adults, and the vaccine was safe. It was effective at eliciting strong initial antibody responses in almost everyone. But the exploratory analysis, when they broke it down by sex assigned at birth, that revealed, finding number 1, a profound difference in neutralizing antibody potency.
And we have to emphasize this number because it's just unprecedented. Female-born participants develop significantly more potent autologous neutralization over time compared to the male-born participants.
Wait, stop right there. When you say significantly more potent, let's put a spotlight on that data. At 10 weeks, after only the second dose, researchers reported a startling 22-fold difference in neutralizing antibody titers.
Favoring females.
22-fold.
22-fold. I mean, to give you some context, in vaccine research, seeing a difference of 20 or 30% between groups is notable. A 2-fold difference is massive. A 22-fold difference it's almost unheard of in a healthy adult population study.
So this is not comparing a pea shooter to a regular gun.
No, this is comparing a pea shooter to a rocket launcher in terms of immune firepower at that crucial early stage.
And while that difference softened a bit over time, it was still enormous. A 6-fold difference even after the third dose at 26 weeks. And the differences remained statistically significant 72 weeks out.
Right, which suggests a fundamental difference in the speed and the intensity of that initial immune mobilization.
Which is a finding that immediately forces scientists to ask, why? What did the detailed analysis tell us about the quality of the immune response beyond just the quantity of neutralization?
And that brings us to finding 2, which is related to a subtle difference in the immune battle plan, specifically looking at IgG subtypes. Yes. They observed differences in the types of antibodies being produced. Females had higher levels of immunoglobulin G subtype 1, or IgG1. IgG1 is generally associated with strong effector functions. It's really good at flagging down other immune cells and triggering a cascade of destruction.
And the males?
The males, conversely, produced higher levels of IgG4.
And what does IgG4 tell us?
Well, IgG4 is often a sign of what's called progressive class switch recombination. It's involved in immune tolerance, and it's sometimes associated with long-term sustained responses, but it's less effective at immediate neutralization or triggering that rapid destruction. So it suggests a qualitative divergence in how their immune systems were prioritizing the response.
This sounds complex, but it suggests the female system was programmed for a faster, more immediate, more aggressive defense.
Right.
While the male system was maybe setting up a different longer-term infrastructure. But this leads us to the most counterintuitive part of the study. Finding 3, the contradiction related to somatic hypermutation, or SHM.
This is where we need to slow down, because it really challenges conventional wisdom. Somatic hypermutation is the process where B cells, your antibody factories, they fine-tune their antibodies in what are called the germinal centers. It's a measure of how hard the immune system is working to improve the quality of the response over time.
So if females had the 22-fold more potent antibody response initially, logic would suggest they should have a much stronger SHM signal. But the data showed the opposite.
Exactly the opposite. SHM levels in memory B cells were significantly higher in males. They peaked around 6.4% at 48 weeks, compared to females peaking around 4.3%. It seems to fly in the face of the potency data.
Why would the males, who started so slow, show signs of a stronger, longer-term B-cell maturation reaction?
The analysis offers a crucial distinction between 2 types of antibody responses. High neutralizing antibody titers, especially early on, are often driven by what are called plasmablasts. These are short-lived, high-output antibody factories that rapidly flood your system with product.
So plasmablasts are like rapid cash flow, quick money in the bank.
That's a great way to put it. And SHM, SHM reflects the activity within the germinal center. That's the area where B cells are undergoing careful selection and refinement to become long-term memory cells. This is a sign of long-term immunological investment.
The retirement bank account.
The retirement bank account, exactly.
So, to use your analogy, females had massive initial cash flow, the plasmablasts, the high initial antibody titer, but maybe less long-term investment, the lower SHM. Males, meanwhile, had a slower start in cash flow, but were building a stronger, longer-lasting bank with higher SHM.
That is precisely what the researchers hypothesize. The male immune system may initiate a longer, more sustained, and more metabolically intensive germinal center response. And that would explain why they eventually start to catch up in potency later, while the female response is characterized by that rapid, intense, high-output initial phase.
This complexity means we can't just look at one marker to declare success. You need the full picture of both the short-term firepower and the long-term investment strategy. But what's the trigger for this fundamental divergence? It seems to come back to that high-dose adjuvant, MPLA.
Yes, the mechanistic link is fascinating. Researchers investigated the innate immune responses, your body's immediate nonspecific defenses, and they found that cells derived from females, specifically monocytes, secreted a significantly stronger cytokine response after they were stimulated with the MPLA adjuvant.
And which specific cytokine were they looking at?
Interleukin-6, or IL-6. This is a critical signaling molecule involved in B-cell maturation and antibody responses. Following the second vaccination, the IL-6 response in female-derived cells was measured as 4-fold higher than in males.
That is the smoking gun. The high-powered alarm bell, the MPLA, triggered a disproportionately strong IL-6 response in females, which in turn fueled that rapid, high-output, plasmablast-driven neutralizing antibody response.
The 22-fold difference. And here's the context that explains why we have never seen this before. The dosage of MPLA used in this trial, 500 micrograms, was massive. It was 10 to 20 times higher than the dosage you'd find in other licensed vaccines, like Shingrix.
So previous vaccine trials, they might have seen smaller, unremarkable sex differences using lower adjuvant doses. But when they cranked the immune alarm system up to level 10, these inherent biological differences between sexes just became dramatically apparent.
Exactly. The trial inadvertently stumbled upon a massive immunological difference simply by using a dose high enough to truly push the innate immune system to its limit.
The implication for global health policy is just enormous. If you look at the epidemiology, young women and girls account for 45% of new global HIV-1 infections, and that number surges to a staggering 63% to sub-Saharan Africa in 2024.
This finding urgently mandates that sex-based differences have to be primary considerations in vaccine and adjuvant design. If a high dose of a potent TLR4 agonist like MPLA can induce this level of robust response, then this tailored adjuvant regime might be precisely what the population most affected young women and girls stands to benefit from the most.
It demands an approach that accounts for biological nuances to maximize efficacy.
It's essential.
That incredible scientific potential, the ability to tailor a vaccine to the needs of the most vulnerable population, it just contrasts so sharply with the extreme human challenges that volunteers face on the ground.
We now move to the community perspective. Specifically, a qualitative study published this November focusing on female sex workers participating in the Phase I pre-PFAC trial in Dar es Salaam, Tanzania. And this section really underscores that scientific success is meaningless without the trust and the safety of the volunteers. Trial participation here involves navigating immense social, personal, and legal risk, especially since sex work is illegal in Tanzania. So the study looked at the dynamics of disclosure, who volunteers told about their participation, and what the consequences were.
Let's start with why they felt compelled to tell people the intended disclosure.
The motivation was really practical. It was about adherence. They needed a support system. Taking daily pills and attending frequent visits requires logistical help, like storing the pills safely, getting timely reminders for appointments, or just having someone understand why you're going to the trial site so often.
So disclosure became a compliance mechanism. One volunteer actually said that her mother, brother, and aunt supported her, and if she forgot the date of her attendance, they would remind her the day before.
Precisely. Disclosure was about mitigating the risk of dropping out or failing adherence. But the real tension arose from unintended disclosure, circumstances that forced them to reveal their involvement against their will, often due to poor studied design elements.
That detail about the packaging is heartbreaking. The audible noise of the pill container, the chaka 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 sound being the giveaway.
It's an environmental clue that carries enormous stigma. That sound, according to the sources, immediately associated the pills with antiretroviral drugs, ARVs, used by people living with HIV. So the sound of the container, a basic design choice, inadvertently led to involuntary disclosure.
Which is a critical ethical failure in trial logistics. It forces volunteers into a high-risk situation.
It does. And once they were forced to disclose, the fear was that they would be misunderstood. They weren't taking ARVs, they were participating in a prevention trial. But that nuance was completely lost in the community.
The fear was that partners or family members would just immediately jump to the conclusion that they were already HIV infected.
Yeah, one volunteer described this massive conflict with her boyfriend, who saw some skin patches, which could have been anything, and immediately claimed she had HIV, asking her, now, what if he sees the pills? This confusion between prevention trial participation and confirmed HIV status was constant and corrosive.
So the consequences of not disclosing were logistical. You had no support. The consequences of disclosure were social and legal, including the fear of exposing their status as sex workers, leading to legal consequences or just immense familial shame. One volunteer feared causing hypertension in her mother if she connected the trial to her occupation.
And this fear led to concealment. It meant volunteers had to lie to their partners, pretending they were going for normal attendance just to maintain adherence, knowing that if they revealed the truth, they would be told to drop out of the study.
But the core challenge they faced, which highlights the massive trust deficit researchers have to overcome, was this deep community misinformation. The perception that the trial team was deliberately implanting the HIV virus through the vaccine.
This rumor was so toxic it caused people to drop out. Volunteers reported friends believing the researchers inject you with HIV through those injections. It's profoundly difficult to ask people to engage in scientific altruism when they're facing a community-wide belief that they're being used as human guinea pigs to be deliberately infected.
And the rumors weren't just limited to infection. They ranged into the bizarre, detailing fears about long-term health consequences, kidney and liver problems, infertility, cancer. But then we hit the extreme end of the misinformation.
Yeah. The sheer psychological distress of the rumor that volunteers would turn into a chimpanzee.
A chimpanzee.
Or that the study team would harvest their kidneys and their livers. I mean, this level of fantastical fear speaks directly to a historical, deep-seated anxiety about foreign-led medical interventions, an anxiety rooted in a complete breakdown of communication and trust.
It calls back to the importance of that "nothing about us without us" mantra that we're going to discuss later.
Yeah.
When volunteers are being told they will transform into an animal, the educational and ethical safeguards have clearly failed to penetrate the community.
And the outcome was immediate discrimination. Because they were perceived as being HIV positive, volunteers were often socially isolated. Reports included being forced to relocate, being assigned a separate room to sleep alone, and being told not to share water glasses, spoons, or plates.
The lesson here is that scientific data is only half the battle. This qualitative study is an essential reminder that every protocol, down to the sound of a pill container, must be designed to mitigate social harm and protect the autonomy and privacy of volunteers who are putting everything on the line to advance global health.
Exactly. Without robust community education, the best science in the world can be defeated by a single rumor or a simple design flaw.
Now we connect that cutting-edge science and the difficult community context to the broader global reality of November 2025. This section explores the profound policy and financial turbulence, making it incredibly difficult to translate breakthroughs like that 22-fold antibody difference into widespread benefit.
And the global health community knows exactly how bad things are. The theme they chose for World AIDS Day 2025 on December 1st is highly telling. It's overcoming disruption, transforming the AIDS response.
Overcoming disruption.
UNAIDS reports confirm that new global HIV infections, they stayed flat in 2024, which means current resources are already failing to drive the necessary decline even before the catastrophic funding cuts we saw.
And the biggest financial news hit this November with the Global Fund's 8th Replenishment Summit in Johannesburg. This summit was aimed at securing the money needed for that critical 2026-2028 cycle to fight AIDS, TB, and malaria.
That was the bottom line.
The results were devastatingly short of the goal. Donors pledged $11.34 billion, While that's a huge sum, it fell substantially short of the $18 billion target that was identified as necessary.
18 billion.
$18 billion. That's what was needed to sustain current programs and, crucially, to roll out new scientific advances like long-acting HIV prevention, new malaria tools, improved TB treatments at speed and at scale.
So we have the scientific tools ready to be mass-produced and deployed, like the mRNA platforms and the targeted adjuvant regimes we just discussed. But the global funding mechanism has just signaled it can't afford the ambition.
Precisely. The shortfall cripples the ability to translate innovation into equitable global impact. The U.S. pledged $4.6 billion, which is actually a decrease from the previous cycle's commitments. And while the U.S. is still the single largest donor, this decrease puts immense pressure on Congress and on other donors to close that multi-billion-dollar gap.
And this deficit is compounded by the severe political disruption we witnessed in the U.S. global health approach earlier this year. The source material refers to this disruption as being deliberate and rapid.
It was. In January 2025, an executive order signed by the incoming U.S. president imposed a 90-day freeze on USAID funding globally. This was immediately followed by reports of a systematic dismantling of USAID by a new entity, the Department of Government Efficiency, leading to the termination of most of its projects.
The source material uses very strong language, calling the implementation of these cuts deliberately disruptive and sadly designed to be cruel. What rationale, even if we're just reporting on it, did the sources provide for such an instantaneous dismantling?
The stated goal of the Department of Government Efficiency, according to its proponents in the source material, was rooted in a belief that foreign aid was inefficient or redundant or susceptible to corruption, and that massive immediate consolidation and termination were necessary to ensure that any remaining funding was applied with maximum efficiency and oversight.
Albeit through drastically smaller mechanisms.
Exactly. But regardless of the intended efficiency, the real-world impact was catastrophic, especially in regions like South Africa, which is a global hub for HIV research.
The impact was instantaneous chaos. Several large U.S.-funded projects were terminated overnight. This included crucial HIV vaccine development, led by Professor Glenn DeGray, and key HIV prevention research by CAPRISA. CAPRISA, in particular, received a physical stop work order in January 2025, followed by official termination for good just a month later.
So this wasn't a slow winding down, it was an amputation. Professor Salim Abdul Karim, the director of CAPRISA, highlighted that, along with major research, feeding programs, shelter projects, and daycare for abandoned children also just ground to a halt. The disruption created a vacuum of trust and funding.
The reaction from African scientists, though, it showed real resilience. Instead of waiting for the political tide to turn in the U.S., leaders like Abdul Karim committed to forge ahead on a path that is more affordable, sustainable, and fundamentally independent of reliance on disrupted foreign aid.
They realized they had, and I'm quoting, zero time to wallow in this grief.
Right, and they immediately began pivoting to non-U.S. grants and domestic solutions. The disruption forced a shift towards self-sufficiency and greater scientific autonomy.
And as the U.S. global health role shifted so violently, how is the fight progressing in Europe?
Well, a report from the ECDC and WHO, dated late November 2025, confirmed that the EU-EE region is also currently off track for meeting the goal of ending AIDS as a public health threat by 2030.
And despite a small decrease in new diagnoses in 2024, about 24,000, a 5.7% drop, what are the key deficiencies in these high-resource settings?
They face critical gaps in testing and late diagnosis. Approximately 1 in 14 people are unaware of their HIV status, and nearly half, 48.0% of diagnoses are made late. And late diagnosis means worse long-term health outcomes for the individual, and it means continued transmission in the community.
So even in well-resourced areas, sustained efforts in prevention, testing, and linkage to care are critically insufficient to meet that 2030 goal.
That's right.
When we look at the immense policy and funding challenges, it's easy to feel defeated. But it's crucial to step back and realize that the decades of massive global investment and struggle in HIV science have delivered monumental benefits that extend far beyond HIV prevention itself. They've fundamentally shaped the entire landscape of modern biomedical research.
This legacy is profound. First and foremost, HIV research pioneered patient-centered science and activism. The crisis of the 80s and 90s forced activists into the conversation, demanding inclusion under that famous motto, "Nothing about us without us."
And that activism created institutional structures that are now standard globally. community advisory boards, ensuring the inclusion of women and minorities in research, making community input into protocol design a prerequisite. This whole model was perfected by HIV researchers.
And that approach now sets the standard across fields, including cancer research. Researchers stopped treating patients as subjects and started recognizing them as volunteers, participants, and drivers of research success.
Beyond ethics and process, HIV activism fundamentally reformed the FDA in clinical trial design. Our sources confirm that the pathways we use today for accelerated drug approval and the acceptance of surrogate endpoints were driven directly by HIV advocates focused on survival.
Right. Instead of waiting years for a drug to prove it extended life, activists demanded that biomarkers like viral load, which predict therapeutic benefit, be used as acceptable surrogate endpoints to speed approval. And this approach is now standard practice in oncology, allowing cancer researchers to test new therapies much faster using endpoints like progression-free survival.
The HIV field also generated entirely new analytical techniques that are used today across vaccinology.
The perfect example is sieve analysis. This sophisticated statistical technique was pioneered to understand what an HIV vaccine actually does. Researchers compare the genetic properties of the virus found in vaccinated people who still get infected versus the viruses found in the placebo group.
And this tells them precisely which strains the vaccine protected against and which it failed to stop.
Exactly, and that informs the design of every subsequent vaccine, whether it's for HIV, influenza, or other complex targets.
And the success of existing HIV prevention methods, specifically pre-PP, forced a revolution in statistical trial design.
It did. Since pre-P works so well, it's no longer ethical to compare a new prevention treatment, like a long-acting injectable, to a placebo. So scientists were forced to design these complex non-inferiority trials, comparing a new treatment to an already highly effective standard treatment. And this shift revolutionized how statistical power and impact are measured across all of prevention science today.
The most dramatic and recent example of HIV's legacy, of course, is the rapid global response to the COVID-19 pandemic.
The entire operational infrastructure for rapid vaccine development, the global clinical trial networks, the expertise in handling novel pathogens, the regulatory flexibility, all of this was the research kitchen established and maintained by HIV researchers. When SARS-CoV-2 hit, they were ready.
That pre-existing infrastructure allowed genetic information to be plugged into the pipeline immediately, facilitating the rapid development and testing of COVID-19 vaccines and monoclonal antibodies in less than a year.
And had that HIV-built infrastructure not been in place, the world would have faced a catastrophic delay of several years.
And the utility goes right down to the molecular level. Drug repurposing is a clear benefit. Ritonavir, originally developed as an HIV antiretroviral, is a key component of the SARS-CoV-2 treatment, Paxlovid.
And furthermore, the systematic, sophisticated approach to designing combination antiretroviral drugs led directly to the development of direct-acting antivirals that effectively cured hepatitis C.
So, hepatitis C eradication is a direct scientific dividend of the investment in HIV research.
Exactly. And finally, the immense insights we gained into T cells, the cellular soldiers of the immune system, have had profound implications for cancer treatment.
We're talking about next-generation immunotherapies like T cells.
Correct. The insights garnered from studying how HIV attacks T cells underpin the development of cellular immunotherapies, specifically CRR T cells, where T cells are genetically engineered to fight cancer. And the technology used to genetically engineer those CRR T cells involves lentiviral vectors, a tool honed and made safe using knowledge gleaned directly from studying the HIV virus.
So the philosophical idea of curing latent lifelong viruses was birthed in the struggle against HIV. And the technological tools refined to that effort are now curing hepatitis C and actively fighting some of the most difficult cancers. The investment has paid monumental dividends across the entire biomedical landscape. This deep dive into the November 2025 news cycle reveals a powerful dual reality. On the one hand, the science is operating at an unprecedented velocity, offering tailored solutions. We've seen the proven potential of nanoparticle and mRNA platforms for precision priming, and the CONEM SOSP40V7 trial provided game-changing data that 22-fold difference in neutralizing antibody potency favoring females when using a high-dose adjuvant.
And these breakthroughs are not academic. They are specific blueprints for prevention in the populations most in need. The data on sex-associated differences reminds us that biological variation is a factor we absolutely must harness. Tailored adjuvant regimes could be the crucial variable for young women and girls in sub-Saharan Africa, the community most acutely affected by the epidemic.
Yet all this scientific readiness is being severely threatened by political and financial instability. We documented the massive $6.66 billion shortfall in the global fund replenishment and the deliberate disruptive termination of vital African research projects earlier this year due to U.S. policy changes. The chaos in funding creates an existential threat to the equitable rollout of these new life-saving tools.
The failure to resource the global response fully means we risk having the technological capability to end the AIDS epidemic, the tailored precision tools, but lacking the political will or the financial pathway to actually deliver it to the people who need it most.
So what does this all mean for you, the learner? It means the fight against HIV is operating at maximum scientific velocity, but is hitting historical political resistance. We know exactly how to develop a better weapon, but we're choosing not to resource the supply chain.
The source material is explicit. The highest concentrations of new HIV infections globally are among young women and girls in sub-Saharan Africa. They represent a staggering 63% of new infections in 2024. Given that the new research strongly suggests a tailored, high-dose adjuvant approach like the high-dose MPLA might significantly benefit the female immune response. The documented failure of global funding efforts, the global fund shortfall, and the termination of vital African research projects, it creates an almost insurmountable barrier between this targeted scientific knowledge and the very populations who stand to benefit most. We have the data to save them, but we are failing to fund the bridge. That is the urgent challenge we face right now.